13.8 billion years ago, before time began and space took form, the entire universe was concentrated into a single point of immense density, known as the Planck density, the only meaningful state before the emergence of spacetime. At this moment, the fabric of spacetime itself is curved and compacted to its ultimate limit, a limit set by the nature itself, by the very geometry of spacetime. One might imagine a spring compressed to its maximum extent. As it tightens, energy accumulates within the spring, waiting to be released. In a similar way, energy in the universe is concentrated as spacetime is compressed. The fabric of spacetime can curve and compress only up to a certain limit. As that limit is approached, the quantum structure of spacetime resists further compression. Its geometry permits only a finite amount of energy to be contained within a given volume. Beyond this limit, no additional energy can be confined, no further compression is possible. In this extreme state, the laws of physics permit only one outcome: to unbind what has been gathered, to release the immense stored energy in a sudden surging expansion. This turning point, where collapse gives way to creation, is known as the cosmic bounce. During the moment of cosmic inflation, the universe underwent an extraordinary phase of accelerated expansion. In an unimaginably brief moment, a tiny fraction of a second, space-time expands exponentially, stretching the very fabric of the cosmos. The rate of this expansion was so immense that it can be likened to a grain of sand swelling to the scale of the Milky Way galaxy in the blink of an eye. Let us look at the moment of cosmic inflation through the frameworks of physical cosmology. Einstein predicted that space-time is not rigid, but remarkably dynamic and responsive. Its geometry can bend, twist, and evolve without resistance or tearing. This inherent flexibility allows the cosmic fabric to stretch smoothly and continuously, accommodating such rapid expansion. And though this inflatory moment lies far beyond direct sight, its echoes remain. Subtle imprints in the cosmic microwave background image captured by Planck satellite reveal faint fluctuations that reveal how the fabric of space-time stretched during this period. These delicate patterns spread across the sky stand as quiet but profound evidence that the universe once expanded in this extraordinary inflationary burst. As inflation ends, the energy stored within the inflation field is transferred back into the cosmos, creating the first matter and radiation. Much like a stretched rubber band, releasing its stored energy as heat when snapped, the decaying inflation field transforms a freezing empty void into a dense heated soup of high-energy particles. The searing heat dissipates, allowing fundamental particles, quarks, electrons, and neutrinos to finally stabilize into distinct entities. While the exponential burst of inflation has ended, the universe continues to expand at a decelerating but still staggering rate, driven by the immense pressure of its own radiation density. The universe has cooled enough for the strong nuclear force to take hold. Quarks are no longer free. They are bound together in the set of three by the relentless exchange of gluons to form the first protons and neutrons. This marks the formation of the atomic nucleus, the dense core that accounts for over 99.9% of an atom's mass. Peering deep within the heart of an atom, we find quarks bound together by the relentless exchange of gluons. This subatomic interplay is the source of the strong nuclear force that defines all matter, including us and everything that we see around us. The universe has cooled even further, allowing electrons to finally slow down enough to be captured by protons and neutrons. This process, known as recombination, creates the first stable hydrogen and helium atoms, marking a transition from a chaotic plasma to a neutral gas. Since the creation of the universe, light photons were trapped in a dense fog, relentlessly scattered by colliding free electrons, a natural characteristic of electrons to deflect light. Only now, as electrons are finally bound to nuclei, does the universe become transparent. Light can finally travel freely across the cosmos, creating the first image of our universe, the cosmic microwave background. This extraordinary image of the baby universe, captured by Planck satellite, reveals the oldest light, dating back 380,000 years after the Big Bang. Released when cosmos first became transparent, these colors represent minute temperature fluctuations, the primordial seeds of density where gravity eventually sculpted stars and galaxies of the universe. The colors in CMB image are a map of tiny density ripples in the early universe. Over billions of years, gravity amplified those ripples to form the galaxies, clusters, and the cosmic web we see today. Hotter and denser regions are the red and yellow sections, more matter and radiation trapped within them. These regions later became galaxies and galaxy clusters. Cooler regions are the blue sections, slightly less dense, matter flown away from these regions that later evolved into cosmic voids.